Hi again. Welcome back. We're glad to have you for this episode of Ask the SOO. This month's question is a little bit more challenging than what we had last month, talking about what's known as a warm seclusion. But to do that, first we kind of have to go back in time, almost 100 years in fact, to understand the origins of the fronts that we're so used to seeing today. In late 2012, Sandy brought a devastating storm surge to the northeastern coast of the United States, hitting especially hard the states of Connecticut, New York, and New Jersey. One of the reasons given by the media for such a large storm surge was the fact that Sandy, which was originally a tropical storm, transitioned to an extratropical storm and formed what's known as a warm seclusion. Well, warm seclusion is a bit of an advanced topic, but to understand what a warm seclusion is, we need to first go back about 100 years or so to the initiation of the original cyclone model, the Norwegian Cyclone Model. This was the first conceptual model of the typical life of a mid-latitude cyclone. The complete model was first described by Norwegian scientists, including Wilhelm Bjerknes, shown here, and Solberg in 1922, and this model contained 4 stages. First, of course, there's an initial state. The initial state in this conceptual model had cold air to the north, in the northern hemisphere, and warm air to the south, separated by a stationary front. The 2 air masses were flowing in opposite directions, parallel to that front. As a wave on the front begins to form due to an upper-level disturbance embedded in the jet stream, an area of low pressure develops. To the east of the area of low pressure, a warm front marked by the red line with red half circles, and a cold front would form to the west of that wave, the blue line with the blue triangles. A front still separating warm and cold air, but warm air was starting to make progress into the colder air to the east, and the colder air was starting to make progress southward on the west or backside of the wave. In stage 2, as the wave begins to intensify, we notice that the warm air is now moving further to the north ahead of the cold front to the east side of the low, whereas the cold air is wrapping all the way around on the west side, and the cold air was driving southward and eastward behind the cold front. So you had an area of warm air to the south and east of the low center, and then you had colder air both to the north of the warm front and to the west of the cold front on the back side. Because the cold air was denser on the back side of the front, it would start to overtake the warm front. Then we'd move into stage 3, where we now see 3 fronts on our map. The warm front, the cold front, and now a new front in the purple called an occluded front. And this area is where the cold front on the west side of the low has now moved fast enough so it overtook the warm front to the east side of the low. The occluded front is now separating 2 different cold air masses, one to the north of the warm front and one to the west of the cold front. So now your warm and moist air is beginning to become confined further away from the area of low pressure in that wedge to the south of the low. Finally, as we move on to the 4th stage, which is what we call the transitioning from the mature to the dissipating stage, that area of low pressure is becoming very far removed from the warm air and instead is surrounded by cold air. You have cold air to the east of the occluded front, cold air to the west of the cooled front, so you no longer have the warm, moist, unstable air mass that helps lower pressures and develop the area of low pressure. So at this point, the low begins to weaken. This polar front model still lives to this day on television, newspaper, and other sources of weather maps, including within the National Weather Service. Further advancements in science, however, have shown that some of the tenets of the Norwegian cyclone theory are not completely accurate. Since the initial postulation of the Norwegian cyclone model, significant advances have been made in the science of meteorology. There's been a large increase in global ground and atmospheric observations. We've had the invention and proliferation of weather satellites. We've also had a significant improvement in our understanding of what goes on in the atmosphere. And finally, the computer was developed, and our increase in computer power and our ability to run sophisticated computer models has increased greatly. So let's fast forward to 1990. Shaprio and Keyser, two very prominent meteorologists in our field, suggested that some revisions were needed to the frontal cyclone model forwarded by the Norwegians. These suggestions were based on the results of both robust numerical simulations and some well-documented field studies in the 1980s, including Gale in 1986, ASP in 1987, and Erica in 1988 and 1989. The Shaprio and Keyser cyclone model also had 4 stages. The first stage is very similar to the stage the Norwegians put forward, where you have a wave of low pressure that develops on a stationary front due to an upper-level disturbance. You have a warm front that extends to the east, a cold front that sags to the west, and these fronts separate the warmer air to the south and the colder air to the north. Again, this is in the northern hemisphere. Now things start to separate a little bit from the Norwegian model as we move to stage 2. There is a development further of the area of low pressure, but instead of the warm front and the cold front remaining locked together, the warm front actually separates some from the cold front. So now you have the area of low pressure with the warm front extending to the east, and it's also trying to sneak back a little bit to the west. Meanwhile, the cold front has actually separated somewhat into a T-bone type structure, and you wind up with warmer air surging to the north and even to the north-northwest ahead of the front. Meanwhile, the cold air to the north is starting to circulate around on the west and southwest side of the low, back behind the cold front. As we reach a mature stage 3, we now see that the warm front extends all the way back well to the southwest of the low, indicating that that warm air is starting to wrap into the low. Cold front is still somewhat separated, and that warmer air that's to the south and the east of the area of low pressure actually starts to feed directly in towards the area of low pressure. Meanwhile, the cold air circulates around the outside of the area of low pressure, again surging behind the cold front. So we have no occluded front in this particular model. As we move to the final 4th stage, we want to notice first that there's a small little pocket developing between the bent back warm front and the cold front of some warmer air. This is the beginning of the warm air seclusion. In the 4th stage now, the bent back warm front starts to wrap all the way around the area of low pressure. The cold front has broken and moved well to the east of the area of low pressure, and we get a pocket of warm air that's trapped near the center of the low. This is known as the warm seclusion. We have warm air to the south and southeast of the area of low pressure ahead of the cold front, but south of the warm front. We have the bent back warm front that circulates all the way back around the area of low pressure. Cold air will circulate around the outside of that and surge in behind the cold front on the south side of the low. Well, why is this so important when it comes to winds? Let's look at a closer up version of this stage. What I've also drawn on this besides the front and the low are the black isobars, which are lines of constant pressure. Where these black isobars are tighter or closer together, it indicates stronger wind fields. So in this model, we have 2 areas associated with this low pressure that form the stronger wind fields. One area is to the north of the warm front, where we get strong easterly winds. The other area is to the south of the bent back warm front on the south side of the low. And we can get some very strong winds in these. In fact, this area of low pressure is often associated with hurricane force winds in the open Atlantic. So now let's take a look at this structure laid on top of winds with Sandy. There's our area of low pressure, which was now beginning to transfer from a tropical to an extratropical system. We have a belt of strong winds to the south side of the low and a belt of strong winds to the north side of the low. The belt of strong winds on the north side of the low are moving in from the east, piling up water into the areas along the coast of New York, New Jersey, and into Long Island Sound. So the combination of strong winds, low pressure, the unusual movement of the low towards the coast, and other oceanographic effects led to the very large storm surge that devastated the northeast coast. Thanks again for joining us, and we hope that you continue to send in your questions on Facebook, Twitter, and YouTube. We'll see you next month.